Welcome back. In our last video, we talked about data pre-processing. In this video, we are going to go into variance-bias trade-off. Now, every estimator, be it linear regression, be it support vector machine, has its advantages and drawbacks. Now, generalization error can be decomposed basically into bias, variance, as well as noise. The bias of an estimator is its average error for different training sets. So bias really is the errors. Variance of an estimate indicates how sensitive it is to varying training sets. Noise is really the property of the data itself. Now, because bias and variance are inherent properties of estimators, and we usually have to select a learning algorithms and hyperparameters so that both bias and also variance are as low as possible. Now, another way to reduce the variance of a model is to use more training data. However, you should only collect more training data if true function is too complex to be approximated by an estimator with a low variance. Now, these are extracted from scikit-learn, as well as this simple example here. This is a simple toy example just to highlight a couple of things. This is a linear regression and polynomial features. Hopefully this looks somewhat familiar to you. And we're trying to estimate a function which is a cost function here. And then we run through basically three charts to try to actually illustrate underfitting, good fit, as well as overfitting, just to actually illustrate the concepts here. I won't go through these codes in depth. Basically, the whole idea of this is you are trying to actually have an actual function here. We are trying to fit the function using a linear regression with polynomial features. And there are 3 degrees that we're trying to fit. There's the 1 degree fit, 4 degrees, and 15 degrees. Clearly, this should be really obvious. The 1 degree is very likely to be underfitting because we have a cost function, pretty much a wave. 4 degrees, probably quite reasonable. 15 degrees is obviously an overkill. So let's have a look at the chart that has been plotted here. So this is the actual cost function itself with the samples that's generated. The orange line here pretty much is the actual line itself. The samples that's generated are the blue one, so our machine learning algorithm only get to see the blue dots. It doesn't get to see the orange dots. So this model, which is the blue line here, is the 1 degree or degree 1 model, and you can see here the actual mean square error is rather large. It's 4.8 times 10, so it's 40 here. And the degree 4 is clearly much smaller. Sorry, that's -1, so it's 0.4, I should say, is actually right. So if you look at this, you can see that the actual true function is almost being overlapped by the actual model itself, because we are using 4 degrees, and it seems to be a good fit. And if you look at the 15 degrees polynomial, essentially the model itself is trying to fit through every single line. So in order to do that, it's all over the place. Notice that it's trying to actually weave through every single samples that it observes. And with this kind of behavior, it's very unlikely that this will work well when you actually provide more data, okay, and test data. Obviously, degree 4 is going to be the best one. Degree 1, at the very least, it has very bad bias. It's definitely a bias estimator, but it doesn't have a lot of variance compared to the degree 15. This has very low bias, but very large variance. So that's really trying to illustrate the point here of the trade-off between bias and variance. When you overfit, what you get is high variance. When you underfit, you get high bias. What we're really trying to achieve here is this degree 4 here. So having used that example as an illustration, we're going to step into a couple examples, and we're going to import the usual library. And I'm going to introduce to you 2 tools. One is called the validation curve, and the other one is called the learning curve. We'll start with validation curve. Now, the purpose of the validation curve is really for identification of over and under fitting. It plots training and validation scores versus model parameters. So in this case, we are trying to vary the model parameters here, whereas the training and validation score will be highlighted to us. We'll be calculating both of these. Okay, the first one we're going to look at is ridge regression. Hopefully you still remember that this is a regularized linear regression. And we're going to import the usual NumPy. We're going to import this model selection called validation curve. That is an inbuilt function of scikit-learn. And we're going to make use of the iris library as well as importing the ridge regression. I'm going to make use of these codes that is actually provided from the scikit-learn documentation. And later on, once I've illustrated these concepts here, we're going to move into the Boston housing data that we've been playing with, and just to see how these concepts can be applied. So you can look forward to that. It's really a little exercise at the end of it for you. But obviously you need to grasp the concepts of validation curve as well as learning curve. Right, so we set the random seed, we load the iris data set that's provided with the scikit-learn. Iris data set is really flowers. I think I briefly talked about this in one of our earlier videos. Right, so in essence, what this is really doing here is we have downloading the data. Okay, so basically we have XY and we are shuffling the actual data itself, and here the actual parameter that we're actually trying to tune here is alpha. Remember that ridge regression has the alpha being the so-called penalized factor, and this is where you can actually vary it. And here we are looking at a log space from -5 to 2, so at a step of breaking it into 10 steps. So this is log space. Let me just show you how this actually works. And what you can see here is that it's 1 to the 10 to the power -5. This is 6 to the power of 10 to -5, and then obviously step by step all the way to 1 to the power of 1 times 10 to the power 2, so this is 100 here. So it's basically on a step basis in the log space. And what we are running here is the actual validation curve that we have imported from scikit-learn. We feed into it the actual estimator, in this case is ridge. The X, the Y, the parameter name here is alpha, and also the range that we are testing this. Obviously you can actually change this number. And what we are using to actually evaluate this is R2, or the R square. And we're printing the training score as well as the valid score. In the meantime, we're also calculating the train data mean, also the train data standard deviation, meaning the actual models mean as well as standard deviation when it's actually being used to when it's trained on the training data. And when it's applied to the test, we're also calculating to the mean and also the standard deviation. This output is pretty much the actual score of the training and also the validation scores. Right, so and over here, the actual test and also the validation are interchanged, okay, are used interchangeably. Right, so when we actually, the next cell here is really plotting the figure itself. We are plotting the parameters range, and we're trying to fill the actual range itself. I'm going to show you that in a minute. And again, we're plotting the parameter range against the actual test. This earlier one is about the training, against the training, and this is against the test. Again, we're plotting the field. This is actually to give it a band. And finally, these are just the label and also the legend itself. So looking at the blue line is the training accuracy. So this blue line is actually the mean score that we calculated. The band here, okay, the upper band and the lower band here, the blue band is the training plus and minus, let me see, 1 standard deviation. And the green one is the actual validation score or the test set. When the model is being applied to it, it has a larger band and the actual accuracy is lower as well. Well, actually this is not really accuracy, this is more the R square, so I should really label it So I'll just call it R2. All right, so what you can see here really is a couple of things. One is that when it's out of sample, the performance decreases. That's the first thing. Second thing is, remember, when you actually have 10 to the power 0, what you get is actually 1. Over at this point here is when there's no regularization being applied. So basically there's no penalty being applied. And this is where the beginning of the training score start to drop fairly quickly, and the actual validation also drop fairly quickly, and the performance of the so-called model is, as soon as you start applying 0.1, applying penalization or bringing alpha of 0.1, it starts to perform fairly consistently, I think around 0.93 and also the validation score as well. If we can look at the data itself, we can't really tell where the actual penalization is being applied. So can't really tell from printing it purely the training score. We probably should print the alpha to go with it too. But that's quite alright. At least from the charts here, you can actually tell. You can tell that as when you actually applied some form of penalization, roughly about 0.1 onwards, you actually start to get pretty good performance out of your model itself. The alternative is that you might want to increase this 10 to 50 so that you can actually see where the real tilt start to come in. So that's really the basic idea of validation curve. So what we are doing now, the next part is, again, just to reinforce the point here, is that we're going to apply this to a support vector machine. So in this plot, you see the training score as well as the validation score. Remember, training is what we use to train the actual model itself. Validation is really the data sets that the model haven't seen, also called test set or validation set. So we're applying this to support vector machine for different values of the kernel parameter gamma. Again, these are the hyperparameter that's being tuned. So for very low value of gamma, you can see that both the training score and also, let me just run these in the background while we're actually looking at this. You can see that both the training score and validation score are low. This is called underfitting. We weren't able to observe this with the ridge regression, so I'm running this so that you can actually see an example of this, whereby the median values of gamma will result in high values for both the training scores as well as the validation score. So that means the classifier is performing fairly well here. If the gamma is too high, the classifier will overfit, which means the training score will be very good, but the validation score will be poor. So let's have a look at this. Okay, again, we are running the same thing. We're using the digits data set now rather than the iris. Digits here is actually really handwriting. Don't be too concerned about this. You haven't seen this. In the future video, I will cover this. In this case, for the validation here, what is being applied is the support vector classifier. We'll cover classifier in the next section. Again, don't be too concerned with this. The basic idea here really is to actually illustrate how to read a validation curve. Again, I'll revisit these concepts so that these concepts are embedded solidly. So just purely by looking at the validation curve and also just looking purely at the label itself, you can tell already these are the behavior. So over at this part, when the gamma is really low, you can see that this is underfit. So the score drops down to 0.1. So it's really, really poor. Let me see the scores here that's being used. Let me just have a look. Accuracy. Okay, the score being used here is accuracy. So because this is a classifier, so you're looking at a accuracy score. All right, so looking at this, as you start increasing the gamma, so let's get gamma, the performance of the classifier improved, and it reached around 100% perfection or accuracy around 10 to the power minus 3, and then it stay 100%. So that's the training score. And notice that the cross-validation score or the accuracy, again, it's underperformed, or rather, or basically from 10 to the power minus 5 or to a lesser number. What you have is a situation of underfit. The actual, once it goes above around, this is around 10 to the power minus 3, slightly larger than that. What you have here is that you have a situation of overfitting, whereby although the training score is perfect, the cross-validation score starts to drop precipitously. What you have is a situation whereby your model is trained perfectly, can fit through fit the data of the training set really well, but it's overfitted so much that it can't generalize well when it sees new data. So what you have is basically a situation that looks like this that we talked about earlier. When you have the gamma is too small, you have an underfitting problem. When you have the gamma too high, what you have is an overfitting problem. It cannot generalize well when it's actually being shown new data. So that's really the support vector machine here. So that's really the portion or the section on validation curve. I hope you found it useful. When we come back, I'm going to go into the learning curve itself. I want to actually cover this in the next video, and then we'll do both two exercises, one on the validation curve and also learning curve. So I look forward to seeing you in the next video. We're going to cover learning curve in the next video.